Hi everyone, we present our work on Hyperstar, a novel task-aware method to recommend hyperparameters for deep neural networks. Transfer learning to fine-tune a pre-trained model on new image classification tasks requires selecting the optimal hyperparameters like layers to fine-tune, learning rate, etc. This process of hyperparameter selection is quite time-consuming, especially if performed for a large number of tasks. So we have hyperparameter optimization to automate this process through something as simple as random search or more sophisticated Bayesian optimization, hyperband or BUHP. However, these existing HPO algorithms are task agnostic because they execute the same search process for each task without any customization or learning from prior experience. This makes them not fast enough for a large set of diverse new tasks. We introduced Hyperstar as a warm start prior to make existing HPO algorithms task-aware to allow faster search of the optimal configuration. We first built a metadata set comprising of accuracies of multiple tasks for a set of hyperparameter configurations. Different tasks prefer different hyperparameters to achieve the best performance. Now using this metadata set, we trained Hyperstar model in an offline meta-learning phase to predict the performance for each task configuration pair and rank hyperparameter configs conditioned on the task. Then, in the online recommendation phase, when faced with an unseen task, we use the trained Hyperstar model to estimate the performance for the set of hyperparameter configs and produce a recommendation customized for the given unseen task. This recommendation is used as a task-aware prior to warm start task-agnostic HPO to find the best performing hyperparameter config in lesser time. Hyperstar learns to represent tasks directly from raw images. We randomly sample batches of training images that are fed to a convolutional network which aggregates the features that goes through a similarity transformer followed by a visual encoder to generate a batch-level task representation. In parallel, the hyperparameter configurations are encoded in a one-hot manner and fed to a config encoder to generate config representations. Each pair of task config representation is concatenated and fed to the performance prediction network to output the corresponding performance estimate. The objective function of Hyperstar consists of three components. The first is the performance regression that computes the mean squared error between the predicted and actual performance. The second is the inter-task similarity regularization. It uses cosine similarity to push tasks with similar configuration trend closer and tasks with different configuration trend farther in the task representation manifold. The last one is the intra-task variance regularization. Since we operate at batch level, we introduce an adversarial loss to bring the batch-wise task representations closer to a global task representation computed as an aggregate over a sliding window of batch representations. To demonstrate Hyperstar, we formulate a task-aware variant of Hyperband. The vanilla Hyperband algorithm works by randomly sampling a set of initial configurations and performing successive halving to end up with the best performing config. To speed up the search, we replace the randomly sampled configs with the recommendation from Hyperstar and show that the top performing config can be found using lesser time budget or configurations. We evaluate Hyperstar on 10 real-world image classification datasets using leave-one-out testing with SE-ResNex 50 and ShuffleNet V2X1. We compare Hyperstar in the form of task-aware hyperband with vanilla hyperband, BOHP, and performance-based grouping approach from Zhu et al. We perform successive halving-based search using different total epoch budgets. The plot on the right shows the best top 1 accuracy achieved by different algorithms for varying total epoch budgets for places 365 on ShuffleNet. We can observe that Hyperstar achieves comparable or even higher performance in just 25% of the budget required on average by other task-agnostic HPO algorithms. Here are results for SE-ResNex and ShuffleNet for some more datasets. We can again observe that even when the budget is scarce, Hyperstar can find the optimal hyperparameter configuration and hence achieve higher performance than all other task-agnostic baselines for the same low budget. To summarize, we introduced Hyperstar, a task-aware warm start HPO prior. Hyperstar is the first to learn task representations end-to-end from raw images for Hyperstar recommendation. Hyperstar ranks and recommends hyperparameter configurations by predicting performance of configurations conditioned on a given task. Hyperstar makes Hyperband task-aware, achieving optimal accuracy in just 25% of budget required on average by task-agnostic vanilla Hyperband and BOHP. Please visit the given link for code and other resources. Also do check out our paper for more results. Thank you.